You know, when you use a tool like ChatGPT, it can feel like you're talking to a real mind. The answers are coherent, they're contextual, and sometimes they're just surprisingly creative. And it's so easy to just chalk it all up to magic, right? But it's not. It's some seriously brilliant engineering. So let's pull back that curtain and take a look inside the engine that changed, well, everything.
So, that's the big question, isn't it? How do these systems go from just a string of words to generating text that feels human? How do they actually get the context, the nuance, and the relationships between all the words in a sentence? That is the core problem we are going to unpack today.
To really get why the transformer was such a revolution, we first have to take a step back and look at what came before it. For a long time, AI researchers were kind of stuck on a fundamental problem that's tied to the very nature of language itself, its sequence.
So the early models, things like recurrent neural networks, or RNNs and LSTMs, they tried to mimic how we read. They process text sequentially, one word after the next, trying to remember what came before to figure out what should come next. And it sounds logical, right? But it had some major drawbacks.
This one-at-a-time process, it created a massive bottleneck. I mean, think about it. If you're reading a super long, complex paragraph, by the time you get to the end, you might have forgotten a really key detail from the beginning. Well, these models had the exact same problem. They really struggled with long-term memory. And because they couldn't process words in parallel, training them was just incredibly slow.
So yeah, the field really needed a new approach, something that could break free from this sequential chain. And in 2017, it got one. A single idea that would completely redefine how machines handle language.
And this is it. The paper that changed everything, with the simple title, Attention is All You Need. Now, this wasn't just an improvement, it was a total paradigm shift. Researchers at Google proposed a new kind of architecture that didn't just use a little bit of attention, it was built entirely around it.
What they did was kind of gutsy. They just threw out the old, slow, word-by-word method. The transformer architecture completely got rid of the need for recurrence. So instead of reading in a line, it could look at the entire sentence, all at once. And that was the key that unlocked parallel processing for language.
So what is this magic attention they're talking about? Well, think of it like this. When you read the sentence, the robot picked up the red ball because it was heavy, your brain instantly knows that it refers to the ball, not the robot. The attention mechanism gives the AI that same superpower. It lets the model weigh the importance of all the other words in the sentence for every single word it's looking at, creating this rich map of how everything connects.
Okay, so we get it. The big idea is attention. But how does it actually work? Let's pop the hood and look at the core components of this transformer engine.
The central mechanism is called self-attention. And honestly, the best way to think about it is like a tiny, super fast search engine that lives inside the sentence itself. For every single word, the model runs a quick search across all the other words to figure out which ones are most relevant to understanding its meaning in this specific context. This search happens through a three-step process for every word, all at the same time. You can picture it like a lightning-fast conversation at a party. One word sends out a query. It's like it's asking, hey, who here knows something about me? All the other words then present their key, which is like a name tag saying I'm a noun, or I'm a verb, or I'm related to this topic. The model then matches the query to the most relevant keys, and those words offer up their value, their specific meaning and information. It's a crazy fast way to build relationships.
Okay, that query key value process is super smart. But there's a problem. What happens when a single word has multiple relationships? In the sentence, the bank on the riverbank, the word bank means two totally different things. A single attention process might get pretty confused. So what's the solution?
The solution is just brilliant. It's called multi-head attention. Instead of just one self-attention process, the transformer runs a bunch of them in parallel. It's like having a whole team of experts read the same sentence. One head might be focused on grammar, another on what the words mean, and a third might be looking at how subjects and objects connect. Then, by combining all their different perspectives, the model builds a way deeper, more nuanced understanding of the text. So we've got this incredibly powerful attention mechanism, but you need a couple more clever tricks to make the whole engine run smoothly and, not blow up. But wait a minute. This raises a fantastic question. If we're ditching the one word at a time thing and looking at everything at once, haven't we created a brand new problem? How in the world does the model know that the dog chased the cat is different from the cat chased the dog? The word order is just gone. The fix for this is so simple and so smart. It's called positional encoding. Before the words even get to the attention mechanism, a little piece of mathematical information, a vector, is added to each one. This vector basically tells the model its exact position in the sentence. It's like stamping each word with its address, your first, your second, your third, and that gives the model that crucial sense of order without slowing anything down.
And finally, you've got two last pieces that are like the engine's safety systems. As information passes through lots and lots of layers in the network, it can get kind of distorted or even lost. So residual connections create a shortcut, allowing the original info to bypass a few layers and get added back in later. This makes sure nothing important gets lost. At the same time, layer normalization acts like a regulator, keeping all the numbers in the calculations from getting too big or too small, which keeps the whole training process nice and stable.
Okay, so we've looked at all the individual parts. But what happens when you put them all together? Why did this one architecture become the foundation for nearly all of modern AI?
The results were immediate and just dramatic. The original papers show the transformer beating the world's best models at language translation. But here's the real kicker. It did it for a tiny, tiny fraction of the training cost of the older models. All of a sudden, building powerful AI became much, much more feasible.
So, when you sum it all up, the payoff was just massive. That parallel processing meant a huge leap in speed and scale. Self-attention gave these models a deep, nuanced understanding of context that was never possible before. And because the design was so flexible and wasn't just tied to one specific task, it became the go-to blueprint for everything, from language models like GPT to image generation and way beyond. The transformer was really the spark that ignited the AI revolution that we're all living through right now. It moved us from these slow, forgetful models to the incredibly powerful tools we have today. And it really forces us to ask, if this one architectural shift could change so much, what's going to be the next attention is all you need moment that unlocks the next generation of AI?